Okay, so the next unit we're starting is two-dimensional momentum and energy. But before we can do two-dimensional, I need to do a little recap of one-dimensional from grade 11, just for those of you that may have had it second semester from home. So first, momentum. The momentum of an object is dependent upon the object's velocity and mass. Momentum is a vector. It's connected to the object's inertia, okay? And you often hear people saying like it had too much momentum to stop. The letter for momentum is a small p, capital P is power, small p, and the equation is simply P equals mv. So if I was running and you knew how fast, like maybe 5 meters per second, and you knew that my mass was 60 kilograms, then my momentum would simply be 60 kilograms times 5 meters per second, or 300, and the units are kilogram meters per second. Okay, and it's a vector, which means direction is going to be important, and the direction of momentum will be the same direction as the object's velocity. Okay? But in physics, it's not usually an object's momentum that is most important to us, but rather the object's change in momentum. And usually we change an object's momentum by changing its velocity, right? So if you're driving down the street and you see a red light in front of you, you need to bring your car's momentum to zero. We usually do that by bringing your velocity to zero. It's true you could press the eject button on your passenger seat and eject your friend who's sitting there beside you, but it's still not going to bring your momentum to zero. It's going to decrease it, but to bring it to zero, we're going to need to change its velocity. So like I said, it's usually the object's change in momentum that we worry about the most. Now, you often, when you're going to pull out, you often think, like if you see a transport truck coming, you probably stop and think twice about pulling out in front of it. Whereas if it's just a normal car, you might do it with a smaller distance because you know the car will be able to slow down in time if you can't pick up speed. But the transport truck might not be able to, and that's because its mass is so big. It has to change its momentum. So it takes a lot more force to change a big object's momentum than a smaller one. Before we go on to changing, there's often the question of, and I always ask it in grade 11 physics, can a hummingbird have more momentum than a school bus? And the answer is yes. As long as the school bus is stopped, then the hummingbird can just be moving slowly and it will end up with more momentum. Or a bumblebee in a bus, right? Sometimes people say, well, as long as the bus isn't moving very fast, please give the poor bumblebee or the hummingbird a break and have it stopped. And then the bug or the bird will have more momentum. Okay? What if we want to change an object's momentum, though, what do we have to do to it? We have to apply a force, okay? So you think you're driving down the road and the light turns red. So here's the light and it's turning red in front of you, okay? And you're back here. So first it turns yellow and you can think, oh, look, that light's turning yellow. And you can keep driving at the same speed and it's still turning yellow and it's still turning yellow. And finally, when you get like right up here, you can step on your brakes. And if you do that, you need a huge force because you don't have very much time anymore to slow down. Whereas if back here you decided, oh, it's going to be red by the time I get there, you could put a smaller force. You could not have to slam on your brakes and stay in your car on its end. A smaller force over a longer period of time will allow you to slow the car down. So if we want to change an object's momentum, we use something that's called an impulse. An impulse is a capital J. An impulse is equal to the force you apply over the time period you apply it. So it's called the impulse. For those of you in sports, you often are coached like this. Like some of our muscles are such that the maximum force we can apply is limited because we're not overly endowed with a lot of muscles. But if we apply it over a long a period of time as we possibly can, then we end up with a bigger impulse, which will then change our momentum more, because J is equal to delta P. So when you change an object's momentum, you do it by applying an impulse. So back to the sports example, it's why you're always told to follow through. Because if you follow through, then your force is whatever maximum force you can generate. But by following through, you're keeping your bat or your hands or your stick in contact with the ball or puck for a longer period of time. So the delta T is bigger.
Good evening, everyone. It's 7:34, and hopefully parent-teacher interviews online went well this evening.
Okay, you can just ignore that.
And everybody is going
so
to be staying late. And
where does this come from?
Otherwise, hope everyone has a great evening, and we'll see you
This
tomorrow.
comes from Newton's second law, F equals ma. Okay, because we know that A is simply Vf minus Vi over delta T. And if we multiply both sides by delta T, then we get F delta T equals M Vf minus Vi. Vf minus Vi is just delta V. So we have F delta T is equal to M delta V. The F delta T is our impulse, it's J. The M delta V is our change in momentum, delta P. So if J is equal to F delta T and F delta T is equal to M delta V and M delta V is equal to delta P, then they all must be equal to each other. So in grade 11, we did quite a few little problems. You were given the force and the time, and you had to find the change in momentum. You could use any two corners of this square. One other thing that I wanted to say is so usually this is the other equation besides the ones I have boxed up there. But this comes into play with crumple zones too, because what crumple zones on a car do is they extend the period of the collision. They make the delta T longer. The change in momentum, your car has to be brought to rest, so this side stays the same. If you can make the time of the collision longer, then the force doesn't need to be as big, and you have a chance of surviving the collision. Okay, so this is where crumple zones come in. So all of those are from grade 11. The other equation that came from grade 11 was something that was called the conservation of momentum. And it's a law. And what we know is that in a given collision, momentum is neither created nor destroyed. Law of conservation of momentum. So if you had like two billiard balls colliding, maybe number 2 is stationary. So whatever the momentum was of the first one initially, M1v1 initial, plus whatever the momentum of the second one was initially, M2v2 initial, after the collision, they must also be equal. The sum must be equal. So M1v1 final plus M2v2 final. So like maybe after the collision, number 2 goes off this way and number 1 rebounds back. But in the end, the total momentum before, so the P total initial, must equal the total momentum after the P total final. And in grade 11, our collisions were always in a straight line. So our conservation of momentum is M1v1 initial plus M2v2 initial, plus you might have 4 or 5 things colliding. So we'll put a ... in there. And if you have more objects colliding, you just fill in 3 and whatever. And if you don't, you just leave it with the first 2. Plus M2v2 final plus ... What it says is the total before must equal the total after. And it's a law, so that must is strong. But it doesn't mean that they can't exchange it. So the first one could lose, but the second one has to gain. And so the first thing I want you to do today is I want you to do a few examples of one-dimensional momentum. Okay, so there is a sheet posted under Teams on one-dimensional momentum, and I want you to go and do those 4 examples and then come back to the next video where I'll solve them so we can move to 2-dimensional momentum. Okay, so go to the sheet under handouts and under momentum and energy and do the example sheet for one-dimensional momentum. All right, and then I'll see you when you finish.